One more. So good afternoon, everyone. I'm Graham Warwick. I'm the managing editor for technology at Aviation Week. So I'm glad to be with you. And our panel is looking at, as it says, the perspectives on propulsion and energy, but this afternoon's session is a view from the users of that propulsion and the consumers of that energy. And so we have with us today to give their perspectives and then talk about them. We have Jim Peterson, who is the lead for all propulsion development for Boeing commercial airplanes. And if you don't think that Boeing does propulsion, they do an awful lot of the integration. They're responsible for the total integration of the propulsion onto the airplane from working with the engine manufacturers through designing the nacelle and then integrating it with the aircraft. So, and next to Jim, we have Sébastien Remy, who is the director for the Central Research Labs at Airbus Group. He's responsible for all the technologies that are used by the three divisions as now exist of Airbus Group, the commercial aircraft that we all know, plus the helicopters division that we used to know as Eurocopter, and the defense and space business that used to be Astrium, and Cassidian is now a single unit. So Sébastien develops the technologies that they will ultimately use. And then we have Les Kovacs. Les is the director of Executive Branch Affairs for United Launch Alliance. Now, he's the guy who's responsible for ULA for talking to the White House, to the Air Force, the National Reconnaissance Office, NASA, for all things to do with national launch capability, launch boosters, launching satellites. And our final speaker today, panelist today, is John Henderson, who's a Lockheed Martin Fellow for Space Propulsion, and his responsibilities go from designing, developing, flying satellite propulsion systems for the satellites that Lockheed Martin make for commercial missions, military missions, government science missions. So they will each step up and give us their perspective, and then we'll have a Q&A session. And obviously this morning you got the view from the engine manufacturers, and they are the suppliers of the propulsion. And it will be interesting now to see how the folks that have to use those propulsion systems, how they see what they get now and what they want in the future, and which directions they want to push the propulsion and the energy industry in. So to begin, I'll ask Jim to speak up. Excuse me, sorry. Let's work out to do that better.
Thanks, Graham. And thanks for the AIAA giving me a chance to come and talk to you about propulsion systems from the airframe point of view. What I wanted to do today was really think about what is the next generation propulsion systems we're thinking about developing at Boeing, and not just the product itself, but I want to spend some time talking about the product and the people in the industry that make it happen, and then something really important in our industry and propulsion, and that's the environment. For whatever reason, on an airplane, everything gets focused from an environmental standpoint on the engines. You know, we create noise, unfortunately, we burn the fuel. A lot of concern about CO2 and global warming today, so I wanted to spend a little bit of time talking about the environment and how that's affecting some of the goals and challenges that we have. So starting with the product, if you look at the Boeing products today, we're delivering really 3 or 4 products of kind of moderate technology, but they're getting much better. So the 737NG, the 747-8, 787, which was quite a step for us, and the 777. Those propulsion systems today, you know, range in bypass ratio of around 5, the lowest for the NG today, up to about 10 for the 87 and 47-8, not quite that high for the 47-8. And pressure ratios going from, you know, around 30-ish to 50-ish. And so those two things drive the thermal efficiency and propulsive efficiency as we go forward. So as we think about the next generation propulsion systems that we're developing right now, we're really trying to push in an evolutionary way the thermal efficiency. So we're going to go up to about 60 to 1 is what's coming from the engine companies we're working with on the 777X, and the MAX is pushing up quite a bit from where the NG is up to about 50 to 1 pressure ratios. Those kinds of thermal changes in the engine that are so important to efficiency do have a significant impact on how we integrate them with the propulsion systems. Whether we have a no bleed system like the 8.7, how much bleed and what the temperature is and how we integrate it is very important. And as we get to the next generation of propulsion systems, it's really having a bigger effect. And I think going forward, we're going to have to work much more closely with the engine companies in an integrated way from a total energy perspective, and beyond just the next one. So the next generation product, I'll talk a little bit about it, then I want to talk about the people and the environment, but the next generation products that we're looking at is, and how we start the process to do that, is it's really about going out to the airlines and finding out what they need. Is there a place in the payload range diagram where there's a hole in our product line that's something that may be able to expand their revenues? Is there something in efficiency that we could do? So when we talk about the propulsion systems, they really are kind of direct drive, high bypass ratio engines. And I think there's a real opportunity for the next generation propulsion systems to take one step further. And as we go one step further and we get to bypass ratios, I'll say 12 to 16, which is kind of on that evolutionary change of bypass ratios, the integration issues for us to make sure that they're efficient become a much greater challenge. So the products that we've developed, we've had to focus very hard on drag and the overall weight of the propulsion system, because if we don't get the weight and the drag down, then we can't take advantage of the better SFC engines coming from the engine companies. The other thing that we really have to work closely with them on, like I said, the systems integration. So typically the overall engine size as we develop and integrate it into the airplane, kind of gets sized by takeoff thrust, usually hot, high conditions. But as we see the engines coming from the engine companies change to higher and higher thermal efficiency cores and bigger fans, the cores are actually getting so small that there isn't enough bleed source if it's a bled type of configuration, or shaft horsepower if it's non-bled, to be able to offer all the services we need on the airplane, to make sure the passengers are breathing enough, to make sure we've got enough shaft horsepower for hydraulics, fuel systems. And so things are really changing. I think the next generation propulsion system that we're working on, we're looking at other ways to manage the overall energy across the airplane, even beyond what we did on the 787. The 787 really took not just an evolutionary step in systems and propulsion and integration, it took a revolutionary step when we went completely no bleed. I worked on that program from the beginning, and it's interesting when you start a program like that. I was really worried about the starting capability. We had 225 kVA generators. Would they be as reliable as a pneumatic system? And as the product has gone on in service, they have just been remarkable. We managed to get it to the point where we can start with just one generator instead of two. And so the starting reliability of the engines have just been fantastic. So when you're at that threshold of technology jump, sometimes the things you worry about and what actually happens are two completely different things. So the next thing, though, that I wanted to talk about, that kind of sets the landscapes for where our products are going. We're currently forecasting that over the next 20 years, there's going to be over 35,000 single and twin aisle airplanes delivered. About a third of those will be replacements. And so the one other thing with the landscape of where the industry is that I think we got to walk away from is there's a huge amount of inertia in the product line already there. So making significant changes quickly are difficult. So when you talk about goals out in 2020, 2050, it really is the next 20 or 30 years are almost set with the kind of technologies and what we're doing with the airframes. But one of the key things that are going to make that happen, and I think it's an important thing to study as we get ready for our next product, is the people. And the people come in a lot of forms. There's a lot of groups that are interested in providing input in how we do that. And obviously the first one for us is the airline customer. So we go out and we really understand what they want, what they need, how are they going to make money, how are they going to reduce their cost. The other part is obviously what all the manufacturing supply base does. We have to take into account that. The regulators, the research community and academic community, and the passengers. So when we did the 787, when we really focused in on the passengers, we wanted to make sure their experience was better. We lowered the cabin altitude, we increased the humidity. There were some really great things that we were able to do. Increase the window size because the structural fatigue of the windows were better. So those are the kind of tensions within the people that are making things happen. And I came from a session earlier this morning where we talked about the regulators, and the regulatory environment in our industry, in the commercial industry in particular, is changing quite a bit. The rules are really harmonized between EASA and the FAA, and I think there are other players that are going to come into the regulatory environment and really kind of drive our development cost and our development risk, which is really important. So I think there's a real opportunity for us to work with the regulators in a different way than we have been in the past. I think having the regulators part of forums like this would be a really fantastic thing. You know, we talk about technologies, sometimes they're very uncomfortable with, so bringing them early into the development phase of maturing a technology and adapting it to a product is really, really important. So, you know, at the back of my mind when we think about going forward with the next product, do we have those right relationships with the FAA, EASA? I think the Chinese will end up becoming more and more influential in the world as we go forward. So understand that environment, realizing it and going forward as we develop the next product is really important. It feels like I started working yesterday, but the other thing I really worry about now, which is fantastic, is all the people coming in, the younger people coming into our industry. So I think about the airplane that we'll probably develop in the 2025 to 2030 timeframe. Those are the folks that are just graduating from school now. We've got to identify those people that really want to do it well, and push them, you know, into leadership roles. And I was starting as a lead engineer in charge of the V2500 system on the MD-90 a long time ago, and I was just 3 or 4 years out of school. We've really got to take chances on the people coming out of schools and work with academia to identify those future leaders for our industry. Moving on to the environment. The environment is something really interesting for propulsion, I think. And when I think about the environment, I think about it's how we most efficiently take the resources we've got from around the world and apply them to the industry that we're involved in. And for BCA Commercial, you know, we sell airplanes, but the real product that we deliver is people and the payload. And so how can we end up making sure that we do that as efficiently as possible through the whole life cycle of our product? So it's not just fuel burn targets, which drive CO2, but it's, you know, how do we produce the products at the end of the life cycle? What do we do with the products? So Boeing's been working to try to set some clear goals for ourselves, and in 2020 we want to make sure that the products that we're delivering with the whole fleet plus the products that are going to be added to that we're carbon neutral. It's probably not as fast as everybody would like, but when I talked about, you know, the whole fleet size that's out there, very expensive capital expenditure for airline customers, how do we end up affecting that quickly? So getting to carbon neutral by 2020 is a really big goal. And then looking out in the 2050 timeframe, we're trying to get to a point where about half the carbon emissions that we had in 2005. So in 45 years, cut it back. And we look at the technologies out in that timeframe, in that future, if we continue to evolve the high bypass turbo kind of engine or even unducted turbofans, it's not enough to get there on the evolutionary scale we're on in propulsion. We've got to do something different. So Boeing is very involved in different kinds of fuels. You've seen us demonstrate our synthetic fuels with our airline customers around the world. And so the only way we're going to get to a sustainable goal like that is to really have a sustainable fuel supply that can be reproduced, and it's a lower impact on the environment as we go forward. So these are the kind of things that, you know, as a leader in Boeing, what I'm trying to think about is we're trying to develop that next product. We've got to worry about the environment because we do get focused in on heavily by the world, you know, on what we do. I think there's something really great about propulsion in general and in the industry, and And that's that fuel burn is really driving us in a good direction from a CO2 standpoint. It helps the airline, so there's just sort of a natural synergy that way. When I look at the next generation of propulsion system, I don't see it as being a revolutionary change. I really see it as a kind of an evolutionary of, 1990s was bypass ratios of 2, then we went up to 5, and then we're up at 10 about now, and probably around the 15 time frame. I do think when we get up to bypass ratios of 15 and the kind of pressure ratios we're looking at in the engines, there are going to be some unique integration challenges for us. We've got to get the drag out, we've got to get the weight out, got to get the cost out, and it's going to be a different installation challenge going forward. I think that developing the future leaders in our industry is an incredibly important thing, and with each development program, that's really where we end up developing people, getting them on those programs in key leadership positions where they can experience the kind of things that we've all experienced in our careers and get them out there. So I think identifying and spending a lot of time making sure we get a good group of folks coming out. We've got odd demographics at Boeing where we've got a large number of very experienced engineers and a very young group of engineers and a big hole in the middle, and so we've got to figure out a way to fill that hole and get our experience up quickly. I think we do need to worry about regulations in general and how we interact with the regulators. The environment's changing completely just in the last 20 years, and I think we've got to figure out a different approach as an industry with regulation. The rules are good. The methods of compliance are constantly changing. They come late in development programs and put huge risk on our programs. I think we've got to figure out a different way to approach the regulatory industry across the world. The other thing that we're very concerned about is the development cost in general of our programs. It's gone exponentially up over the last 20 years too. We've got to figure out a way to break those development costs, and I think working with the regulators and our own tools and processes will help that. And so that's kind of my view of things. I appreciate your time, and I'm looking forward to some great questions, Graham, so thank you.
Thank you. So before I introduce our next speaker, thank you very much. I think you'll see some words and themes that are going to start to appear, and I think integration is going to be one, and I think people is going to be an important one as well as we go forward. Just to remind you that I think that we have question cards for those of you who would like to submit questions, and I'll ask them. We will also use the microphones when we come to the Q&A session, but if you do have a question, please just fill out a card and we'll make sure we get to your question. So, Sebastian? That's not mine. So, could we get the right one up? I don't think that Airbus does. Well, it does, of course, through Astrum.
Why not? Okay. Ladies and gentlemen, one of the questions I often receive as head of the research labs for Airbus Group is to properly prepare the future of aviation, you need to be an engineer or do you need to be a scientist? Be my guest for the bets. But actually, it's an interesting question. When we look at how the scientific research is conducted, we may look at two different axes. Whether there is a fundamental quest for the physical understanding of the phenomena which are involved, and whether there is a strong focus on an application or not. Of course, if there is neither a quest for the understanding nor an application, there is no scientific research. That's the gray zone, which is of little interest. I would say an engineer will probably be in the quadrant which is called the Edison's quadrant, which is where you are really focusing on the application. You want to have something, a technology that works for your application, very efficient for the application. A pure scientist, a pure researcher would probably be in the Niels Bohr quadrant. He is mostly interested in understanding the underlying physical phenomena or chemical phenomena, but less to an application. It's just quest of knowledge for the knowledge. But actually in our industry, we need both. Just the recipes which are working for a given product It's fine, but how do you generalize the use of that technology to other applications? Just the physical understanding of things is fine, but, well, we are in an industry, and we need to have those applications. So what I would like to show you is that this dimension, which is called the Pastor's Quadrant, is something where we are working and where there are opportunities for the younger generation to be part of. And by the way, we can both advance aviation and serve the benefit of the society. Let's look to slightly longer term than my colleague was discussing just before. There was a survey that was performed in 2012 asking to the people that would be the travelers of the future, what would they consider as the key items in their mind. A third of them say being late and being delayed, and by the way, that was most of the discussion we had just before that session in the VIP room, is the most annoying aspect of air transportation. 2/3 think they are going to fly more than they do. But the overwhelming one, 96% of the people think that air transportation needs to be more environmentally sustainable than it is today. And this is precisely in line with the daunting challenges that we have taken as an aviation industry, that you see there as part of the Flight Path 2050, 75% reduction of the carbon dioxide footprint relative to 2000, 65% reduction of the noise footprint relative to 2000. Can you do that simply by an evolution of the technology? Probably not. You need to unlock other dimensions. One of the dimensions I would like to share with you is the dimension of hybridization, use of electricity for part or all of the propulsive and energy sources on board the vehicles. What you see here is a kind of roadmap of what could be feasible in the near-term future and the longer-term future. We have flown already a certain number of vehicles which are hybrid, which means basically they have some diesel engines which are generating electricity through a generator. We are even today flying a small aircraft called E-Fan, fully electric. 60 kilowatt is the power of the two main engines. It is flying on a daily basis. It has accumulated over 50 flights now. The interesting part of it is both the propulsion and the landing gear are electric. All that thanks to lithium polymer batteries for the demonstrator. And the battery is not anymore a box as you can think it is on the current aircraft. There is no more box. The cells of the batteries are distributed in the various areas of the fuselage and in the wing in order to contribute to the balance of the aircraft. And they are individually instrumented to provide the pilot with the proper information to master them. It's a 10-meter wingspan aircraft, and you could wonder, what is the purpose of that? It's a small aircraft that is dedicated to pilot training. For the initial, I would say 10, 20 hours of training of the pilots, which want to get their private pilot license, they can go on that fully electric aircraft. Just to give you an idea, the noise of that aircraft at takeoff is probably the same way of the same level as my voice at the moment. It's a relatively noisy environment for a restaurant or a room, but it is probably 20 to 30 dB smaller in terms of density than the current aircraft at takeoff. The consequence of that is most of the limitations for the small aircraft operations close to the cities will be alleviated. We are not too much interested in selling those aircraft. Of course, it's a good business. But really, what is of interest there is to get in-service experience of a fully electric vehicle. Because at the moment, everybody is doing the same type of study. More electric technologies on board an aircraft, at the moment, it's additional weight with additional reduction in terms of fuel burn. And depending on the level of technology, like the batteries densities, like the electrical motor generators power density, the balance is positive or negative in terms of fuel burn. But in terms of noise, it's really a winner. This is something that you cannot do with conventional technologies. You don't have anymore the jet effects. You can simulate very high bypass ratios without any problems. And the most important dimension is, for once, you can decouple the energy generation from the propulsive locations. And this opens quite interesting dimensions. Let me give you an example. Today, the tail of an aircraft is sized by the engine out condition. You need to be able to control your aircraft with speed when you lose one engine. If you consider an airplane which will have one generator, providing the electricity and operating multiple fans, then the certification condition of engine out becomes either I lose my gas generator, I operate on battery, but I have a symmetrical aircraft, or I lose one of the fans, but then the asymmetry is very limited. And as a consequence, I can rethink the architecture of my vehicle, get rid of the tail, or put a very small one on top of that. So it's not simply the virtue of replacing a modestly efficient gas turbine by a more efficient gas generator electrical thrust system. It's also rethinking completely the borders between what is traditionally an aircraft and what is traditionally an engine. The border between what today is certified as FAR 33 and FAR 25 is much more blurred. And those certification issues, we investigate them also thanks to a small aircraft. Later on, we will move up, depending on the availability of the technology, depending on our capability to unlock those challenges relative to the battery's energy density, relative to the high voltage network for the electrical system, relative to the electromagnetic compatibility. We will move up in the power range. But one dimension which is essential is we have lived so long with this kind of isolated propulsion system under the wing, separated from the airframe, that the best people to think about the future vehicles are the younger generations, which are not those preconceived ideas of what an engine should be and what an airframe should be. Thank you.
Thanks. Well, I think Sebastian neatly brought together integration and people with that one. And I think some interesting insights into quite how electric propulsion or hybrid propulsion could really change the shape of an airplane in ways we wouldn't expect it to. So, anyways, we will now move from the air into space, and Les will talk to us about the launch side.
Good afternoon, everyone. It would help me to know how many of you out there are rocket propulsion or folks that are interested in rocket propulsion. Just a quick show of hands. Okay, good. All right, so for the rest of you, if you check your pulse 5 minutes into this, you should be legally dead. So what I thought I would do is, there is a specific issue in Washington, D.C. that's actually occupying all of our time. It is some legislation that was introduced on the Senate side, and I'm going to walk you through the implications of what that means for national security. It's not a good picture. This is the second one of these forums previously at NSS. I kind of feel like when it comes to these panels, I'm the delegated wet blanket. All right, so if you talk about only the liquid oxygen RP-1 hydrocarbon class of rocket engines, the U.S. domestic family looks something like this. These are the launch vehicles that dominate the marketplace. So on the far left, you have the Atlas V. It probably launches somewhere between 60 and 70% of the United States' national security missions, spy satellites, GPS, secure communications, meteorological satellites, you name it. The RD-180 engines on the Atlas V produce about 860,000 pounds of thrust. It is the nation's most reliable way to to low Earth orbit or for interplanetary destinations. It actually launched the Mars Curiosity rover. Just an excellent engine. In the middle, you have the Merlin 1D, about 147,000 pounds of thrust. It flies on the Falcon 9 launch vehicle. There's actually 9 of those on the Falcon 9. They're all produced here in the United States. In the interest of, I need to go back real quickly. So the RD-180 is actually manufactured in Khimki, Russia, and it's imported into the United States. And then on the far right, you have the AJ-26. It is an Americanized version of the NK-33 Russian engine that was used for the moon program, or was supposed to be used for the moon program. 2 of those fly on an Antares launch vehicle. They each produce about 336,000 pounds of thrust. So you're up around 770 plus. So that's the state of affairs. So recently, as you know, Russia invades the Crimea. And the first thing that happens is the United States Congress gets upset about that, rightly so. So we want to impose sanctions on Russia. So Congress is pretty irritated about this. So what they did was they introduced language in the Senate that looks like this. It's more famously in DC circles known as the 1623 language. It comes from the National Defense Authorization Act. Now, the key thing for those of you that aren't familiar with this, that act, or the NDAA, is the thing that pays for the Department of Defense. So once this becomes law, it then gets funded, and if you're not in there, you're not going to get money, and your program basically terminates. So essentially what the 1623 language says is that the Secretary of Defense cannot enter into a contract or renew a contract with any entity that basically does business with Russia. So what that means is, depending on the timing of this language, the Atlas V launch vehicle line comes to an end. Right now, it launches the majority of national security missions. There is not enough activity in the civil or commercial sectors to sustain the vehicle, so that's a problem. It is the single greatest problem when it comes to rockets and propulsion that's sucking all the air out of the Washington, D.C. environment for about the last 2 months. We're singularly focused on trying to save the vehicle. Pentagon does not like this. Basically, the entire executive branch is not really a big fan of this language. We're trying to fix it, and it's something that you should all be aware of, and I'll get on to some more specifics here in a second about funding and budgets and things like that. So I included Clause B in there because it says that the Secretary of Defense can issue a waiver to Paragraph A. The reality is that no company is going to actually continue operations if their continuing concern is based on granting of a waiver. We typically need to know 2+ years ahead of time whether or not we're going to get a mission so we can time the production flow and the import of these engines to that. So that's the 1623 language. It was also supplemented by something called the 1629 language a couple paragraphs later in the National Defense Authorization Act. And this one is essentially saying, you know, we recognize that we have neglected the U.S. industrial base when it comes to LOX hydrocarbon engines, and we want to initiate a development program to build a U.S. domestic equivalent, sort of, to the RD-180, something in the 500,000 pound to 1 million pound thrust class. And if you fielded that engine, you could actually put it on any U.S. launch vehicle. So that's the master plan. So typically, there is very little funding when it comes to this kind of activity. So AFRL, you know, I don't want to say they limp along, but they don't have a ton of funding. NASA, same story for propulsion. So this, when you look at the blue takeaway box at the bottom, gives you an idea as to the seriousness of what's going on. On the House side, they've actually said, well, we think you should spend $220 million on this problem. And they're actually looking to appropriate all $220 million. On the Senate side, it's a lot lower. It's $100 million authorized, and of that, only 25 would be appropriated. So there's a disconnect there. If you listen to what folks say about the amount of money it would cost to actually field an engine in this class, the private sector will tell you we can do it for $800 million. U.S. government will tell you it takes somewhere between $1 and $2 billion to field a LOX hydrocarbon engine in that thrust class. So you can tell that the House version of the world is more consistent with what it would take to do risk reduction in an out-year program to field a different engine, right? The estimates to field the engine also range on the private sector side from 4 to 5 years. If you ask the U.S. government, they'll tell you it's probably anywhere from 7 to 9. So we're facing a serious problem when it comes to propulsion. I sort of focused here on the RD-180, but the same applies to the AJ-26 because it's a Russian engine. So essentially 2 of those rockets are in jeopardy. In the AJ-26, and Antares is used for low Earth resupply of the space station. So when you sit back and you think about, okay, we realize that in the nation's interest, it's probably the best thing to do to develop a new engine. And optimally, you would want to fly the one that you currently have until the new one comes online and gets flight certified. So then the question becomes, well, how serious do you want to be about fielding a new engine? What does that story look like? So this slide here is the forecast for worldwide launch demand. So in any given year, worldwide, there are about somewhere between 60 and 80 launches a year. 2013 was sort of typical. We had about that. The range fell in there. I think it was 77 last year. Of the 77 launches, 23% are U.S. launched. The U.S. portion of the market is about 23% of that. Last year, that equated to 19 launches. There were 11 of them that flew on Atlas and Delta rockets. Falcon 9 had 3, and then Minotaur and Antares from Orbital Sciences had 2 apiece, and then there was a Pegasus also from Orbital. So the problem is the business development guys that are looking at this, they're saying, okay, well, 60 to 80 a year, that's pretty typical, and we're going to project that out. However, in 2019, we're going to come up on a historic low for national security launches. Instead of the 10 or 11 per year, the market is going to shrink to something on the order of 6 to 7 a year. So even if you add in NASA's requirement for human launch services, ferrying astronauts to and from the station, which is about 2 launches per year, it doesn't bring you back up to anywhere near where you want to be. And the balance of the slide is 25% of those launches we could get, but typically they're spread around customers. They're international launches that we don't have access to, and they fly on Ariane, Proton, and Sea launch vehicles. So if you're an elected official and you're looking at this, you're kind of saying, well, yeah, we need a new engine. However, it doesn't look so compelling to where you can recoup the costs and investment if you're actually paying for a new engine. So the story is not that great. So the bottom line is looking ahead as to what would happen in this class for engines. Like I told you, $800 million, anywhere up to somewhere between $1 and $2 billion. That's a government estimate. You would not want to abandon RD-180 procurements until a new engine came online. There is no certified launch vehicle in the U.S. inventory that can replace Atlas for national security launches. We currently don't have any indication that there's going to be an interruption to the supply. So all of the stuff that you read, probably in Space News, we are continuing to import RD-180s. We have licenses in hand for the 2 shipments that will occur this year. Those licenses do not have any restrictions on use, so we can use those for national security launches, and we're going to import even more, another 29 engines, over the next 4 to 5 years. So the problem is the Congress has a difficult time looking over the horizon. Right now, this problem is staring them in the face because it's right here. Crimea just occurred 2.5 months ago. So while the funding, the $220 million, looks very appealing in the near term, any kind of an engine procurement is going to last well beyond that. It's going to be 5, 6, 7, 8, maybe even 9 years down the road. So the yellow takeaway box, any product that you're looking to build is well beyond the 2-year budget cycle that Congress looks at. And there's no guarantee of sustained funding. So what I want to leave you with is, it is the right thing, I want to be on the record here, it is the right thing for the United States to develop a LOX hydrocarbon engine in the 500,000 pound to 1 million pound thrust class. It is good for the US industrial base, and the United States should have probably done this 5, 6 years ago, 10 years ago. They didn't. Now we're forced to do it. And so the wet blanket portion of this panel is this briefing. All is not well in the liquid rocket propulsion industry. So I look forward to your questions. It's an interesting time in DC.
Thank you, Les. I think we see another aspect of people, which is Congress, and another aspect of integration, which is clearly the customer having had a long case of neglect in the industry, somehow or other not being able to change the customer's mind about what they thought they needed, and we're now facing the results of that. So extraordinary. Anyway, and to wrap up, we will head over to the man responsible for the thing he puts into space. So
yeah, we're the ballast on his rocket. Did I say that right? Good afternoon. I want to talk to you about something that's my passion and my expertise. So I'm going to try and go present the user's perspective of the technology we use for satellite propulsion. I think it's very important that in order to understand where we're going with respect to satellite propulsion, that we understand how we got to where we are. 100 years ago, today, this month, Robert Goddard patented his liquid propulsion systems. 45 years ago this month, we landed people on the moon and returned them safely. If you take a look from a chemical propulsion system today, you'll see much of the technology that was present on the Apollo spacecraft still being used, still using processes that were developed back in those days, still working using the components and the technologies that were developed back in those days. Very, very well, very reliable systems, but there hasn't been a lot of technology insertion into the platforms that we're currently flying. One area that's counter to that is areas that the Lewis and now Glenn facility worked on for many years, which is the augmentation of chemical thrusters, arc jets, and then, EHTs, and then arc jets, which are still being flown today, where we're adding energy from the satellite, hence the propulsion and energy theme, to the chemical reaction that's going on in the thruster to produce higher efficiencies as far as the thrusters and the systems are concerned. Now that's chemical propulsion. Electric propulsion, 50 years ago this month, saw the launch of a satellite that had 2 ion thrusters on them. They were powered, or their propellant were mercury and cesium, and I think we're still cleaning up some of the environmental effects of that over at the Lewis facility. Again, technology that was developed by NASA and inserted initially into the satellite program. Now, 33 years later, Deep Space One is launched with ion propulsion in it, using xenon as the propellant. And it went on to demonstrate or to produce over 4.5 kilometers per second of delta V for that satellite. The Dawn spacecraft is the next large spacecraft, and it's either has or will soon be imparting over 10 kilometers per second of delta V on the spacecraft. Much, much larger than we would ever get from a chemical system without enormous mass of propellants. So, but it still took 33 years from when the initial ion technology was launched for it to be introduced into exploration, and then since then has been put into routine operation on commercial satellites. Now the Soviet Union and then the Russians have in the intervening years have been launching many, many satellites with this technology on them. basically taking advantage of the high efficiencies of that propulsion system. So that's a brief history lesson in 3 minutes or less. Now, the question that comes up is, well, why does it take so long for us to introduce new technologies or not into our satellite propulsion system? The first thing is that the users are very, very reluctant to make changes. The propulsion system is unique on a satellite in that you cannot fully test the propulsion system before you launch it. It's equivalent to building an airplane and then not testing the engines until you try to take off. And so the customer environment is extremely reluctant to make changes. If it worked last time, why am I making changes this time? The second thing is that the cost associated with developing and proving out a new propulsion system, new technologies, is prohibitive. It basically takes coming up with a mission that the conventional system cannot do, such as Deep Space One or Dawn, where you just can't get there with the system. And now it's worthwhile for us to develop the technologies and introduce them into satellites. And so the key piece of getting technology or new systems into there is that it enables the mission. You could not do it without that technology being, or else you'll be constantly working back with, why can't we just use what has worked successfully for the past 40 years? Okay, so that's the reason for why there hasn't been a lot of change. The next piece is, well, what's wrong with the current state of the art? Well, the first thing is that the spacecrafts we're launching now are many, many times larger and more capable, both in power systems and in the sheer mass of them. And so the costs associated with launching those things with conventional propellants making up roughly half of the satellite launch is prohibitive. We're running out of launch vehicle capability. It's just so expensive for you to field that kind of mass. The second thing is environmental. The hazardous operations associated with testing the rocket engines, testing the components, shipping the propellant to the launch site, going through the hazardous operations associated with the propellants is getting to be extremely expensive for you to do on a routine basis. So those are the two things that are pushing to says, hey, maybe we need to make a change in the propulsion system. So the change that's taking place are from a chemical standpoint, it's trying to move away from the hazardous propellants, the hydrazines, the monomethyl hydrazine, the nitrogen tetroxide, and introduce environmentally friendly and less hazardous propellants into a chemical systems. There are reasons why chemical systems will continue to be built, mainly that you can have thrust as required. It doesn't take a long period of time for you to develop a significant delta V. You can get it very quickly. So they're going to be around for a long time. The fascinating things that are going on in the industry right now are the Han-based propellants, as well as the AFM 315E propellant developments, where significant resources are going into propellants that have the potential for coming up with more environmentally friendly as well as less costly propellants in terms of logistics and getting on the satellites. The issue with those is that, as I went back to my beginning statement, satellite operators are very reluctant to make changes, and we're going to need long-term operational experience to demonstrate that, yes, those propellants can do what they're being developed to do. As far as electric propulsion is concerned, this is where the large amounts of development are going to be over the next, in the near term, where we need higher thrust, which means higher power, which means we need to stop building power boxes and propulsion boxes. We need to start building integrated systems on our satellites that can handle the enormous loads associated with these next development as far as electric propulsion systems are concerned on satellites. So in the long term, I don't know what the system is going to be. It gets back to what mission are we trying to solve and what technologies do we need to develop in order to enable that mission, whether it's asteroid missions, return to the moon, go to Mars. That's really what's going to form the basis for what the next system is going to be. It's what technology do we need in order to allow us to do those missions. And many of the people in this room will be responsible for guiding how what technologies we build in order to be able to do those enablers. And finally, the one guarantee I'll make is that it will be a combination of propulsion and energy that will be that technology or those enablers, because we can't keep taking all the propellant, the chemical propellant with us when we go. We have to augment the chemical, if that's what it takes, in order to do those missions. Thank you very much.
Thank you, John. So, folks, do you, if you have questions, filled out cards, or if you want to step up to the microphone, we're happy. We're going to now have a chat. So, you talked about a lot of different things you're working on in the future. I mean, if you were to look at it now, I mean, obviously you need a customer pull, or you want to call it, to take something forward. How, as you stand now, I mean, you're either looking like a 2-year horizon over on the ULA to a 20 or 30-year horizon. Where would you see your greatest pull or most consistent pull at the moment? And can you say, from propulsion, I know in the airline industry, it's going to be fuel burn. All they're interested in is fuel burn. So as long as I'm driving down that route, I'm in good shape. Or do you see that there may be different factors, or that you have to, you worry about shifts in the customers, the pull coming from a different direction? When you're doing your planning, I mean, how consistent and how sure are you that of where you're going, and what are the things you're being told at the moment that you need to look for?
I mean, first, Les, maybe we can do a little business. I was thinking about using one of those RDL 180s for a 737, but it's a little overpowered. You just get rid of about 450,000 pounds of thrust, and we don't want to carry the oxygen either.
Put it in orbit.
Yeah, put it in orbit. No, I think, if you look, it just came from another industry event where if you look at the rate of change of passengers, it is actually going down. I mean, we're at about 3% per year where the passenger growth is going up, and you look at where the products are being developed for, that's changed things quite a bit too. So, so as the world gross domestic product continues to go up, the world has continued to expand from an economic standpoint. So when we look at our forecast, we look at all of that. So we know that the demand is going to be there. One of the first things that developing areas of the world do with their free money, their free money is to go travel. That's really what they want to do. So, and it's been happening for the last 50 years. We don't see, at least in the near term, any disruptive technologies. There could be some significant issues, as Les mentioned, in the geopolitical world that could slow things down like it did right after 9/11. And so we are continuing to focus our products on getting to be better fuel burn. If you look at what happens with the airlines as they operate the airplanes, on the long-range airplanes, the cost of the fuel is about 50% of their operating cost. On the shorter-range airplanes, it's about 30%, and that's doubled over the last 10 years. So, in the passenger and package carrying business, the economics drive it, and I think the economics are driving it in the right direction for fuel burn, which actually naturally helps the environment because it reduces the CO2 load. So I think there's some natural things that are going in the right direction, but we always are looking out for, disruptive technologies, disruptive geopolitical issues to make sure we're on the right path. But I feel like we're on a pretty good path right now.
Sebastian, you obviously deal with a wider range of markets that you have to anticipate.
I fully subscribe with what you say. There are two dimensions to the fuel burn. The part of it in the operating cost of the airline, as you mentioned, and the volatility. The volatility of the fuel price is a big hurdle for the airlines because they don't know how to bookkeep that unless they are very rich and they have the luxury, which I don't believe there are that many, but they have the luxury to hedge it. So anything which is linked to reducing fuel burn or finding alternatives to fuel burn will help in any case the business. The second dimension, I think, which is very important is environment. We tend to look at it as our footprint as an industry, but we have to realize that this growth factor that we have the luxury to enjoy is still limited by the fact that we'll be able to develop the industry only if we are able to limit the footprint. And this is gaseous emissions, but it's also noise. Otherwise, we will be prevented, especially in Europe, for instance, of any growth, because we won't be able to have additional runways or to operate during certain time of the day in some areas.
When you come to the space side, I mean, is there really any incentive to push ahead technology-wise? I mean, you have an incredibly conservative customer, an incredibly heavy, high safety bar that you have to meet. You get to fly it once,
right,
or you get it to put it somewhere you can't go fix it.
It's
so
extremely
how do you even find any driver to go beyond what you know works?
It gets down to, like I said, it gets down to enabling a mission that you cannot do the Dawn mission without using the ion propulsion that you have on there. You could not do the Deep Space One mission without having that propulsion system on there. It's coming up with a mission that can only be done with something new, so that your return on the investment is essentially infinite. Otherwise, you will spend lots and lots of money and not be able to sell it to anyone as far as putting it on their satellite, because the old way works.
So what drives the technology then? Sorry, I mean, why do you even invest in technology? I mean, are there missions that are evolving that
yes,
are coming?
There are always the next mission. There's always something that we can't quite do with what we have today. And it's a matter of making that mission a priority and then applying the technology that has been, and the physics and the basic science that have been worked out over the decades to that mission to solve it.
So what about on the launcher side? I mean, obviously, the whole idea of the EELV and ULA, et cetera, was assured access to space. It was all about stability and reliability.
Right.
And now we're in a situation where we've gone for decades without investing in a technology we now find we need. Unless, I mean, that's never going to change. We only want what we have now, sort of.
Right, so, the propulsion piece, it stands out singularly because of its cost and complexity. But across the rest of the airframe, there's lots of innovation going on. So we're doing things like common avionics between the vehicle families, improving the primary and secondary structures. So we're trying to drive out efficiencies anywhere we can in manufacturing processes and in the vehicle itself, leaning the company out. The new entrants that are coming into the market, Orbital and SpaceX, they're essentially forcing the market to be more efficient. In a competitive environment, which is what it will ultimately become, it's in the vested interest of the players to be more efficient. So that's what we're doing. But the differences between the airframes and the rockets are, on the rocket side of the house, it is a very deliberate and very slow process to do that kind of stuff. Any significant change to a rocket results in a recertification requirement, and it's just a cost untenable thing to do.
So one of the we have a question from the audience here, which to do with the question is about what is Boeing's electric or hybrid electric propulsion strategy. But I actually want to use that as a lead into about how we do this transition, from where we are today, and the how and the when. I mean, where does Boeing stand at the moment about hybrid stroke electric?
Well, I think, if you look at what we've done on the 787, we really understand the value of developing electrical systems in a different way than we have in the past. How energy gets balanced across the airplane. I think there's some significant, I kind of came today to talk about what's our next generation of propulsion system. And I think the energy density required to do electrical powered flight in a commercial way is just not going to be there in 2025. If you look at the power density of kerosene fuels, it's incredible compared to batteries. And so how do you end up, and you've got to fly the batteries around the whole flight, so you don't get to take advantage of burning off the fuel. So electrical power has two steps that it has to meet. That really high, it has to first meet the electrical density of kerosene fuels, and then it also has to overcome that you've got to carry around the whole thing for the whole flight. And so we are investing in electrical power, in the future technologies, but I just don't see it being really feasible for the next generation, the next 20 to 25. And it is part of our overall strategy to help to get to our 2050 goals of trying to reduce CO2 emissions by 50%. I think, as Sebastian said, it's a fantastic opportunity for noise, and I think that communities will need lower and lower noise as we get higher and higher bypass ratio today. That also goes directly in reducing noise, but I just don't see it in the 2030 timeframe. It's Horizon 2 or 3 out there.
Now, obviously, at Airbus, you have probably a similar time horizon, but you have an opportunity to move more quickly in other markets along that way, because you're serving multiple markets.
Yes, absolutely, and I fully agree this will not happen in the commercial world, in the big aircraft in the 2025 time frame. There are a couple barriers that need to be alleviated. I mentioned the certification. I would like to mention another one in the business model. As of today, fuel burn is a big one. Maintenance cost is also a non-negligible one, especially for the short-haul operations, which happens to be the smaller airplane. Everybody thinks that at some point in time, hybrid electric or more electric will be much better in terms of maintenance cost than the current purely thermal solutions. That is yet to be demonstrated. So what we do is actually we climb up in scale. We start with this small airplane. The next step will probably be a light helicopter, where we are going to use electric assistance for auto rotation or those type of things, because this will be in the range of a couple 100 kilowatts, which are not too far away from what we can do today. To access commercial aircraft, even the smallest one that we have, we are talking tens of megawatts of power. That's another dimension. But it will exist only if we are able to unlock the certification dilemma. How do we certify those configurations? Today, even if the technology solutions would be there, we would not be able to do that because there is no certification base. Two, if we are able to demonstrate through in-service experience of lower power vehicles that we have indeed the in-service experience to consolidate the maintenance cost equation. And three, if we can find the technology barriers which are linked to the batteries and the electrical motor generators, I would say those are the two key ones. But it's a progressive one. It will not happen overnight, and it will not happen overnight even if the technologies are there for the big ones, because there are several steps to be climbed first to unlock those certification and technology issues.
What about, you two obviously are linked to the hip when it comes to this, because if he can make a lighter satellite, then you can launch more of them, or even two of them at the same time, or something like that. But I mean, are we finally getting traction in electrical propulsion in the satellite side, and do we have a similar sort of phased way we get from where the electric, and you then go to a more integrated platform, and is there a way to do that?
I wish it was more methodical and planned, but because market changes, particularly in the commercial area, really drive the overall architecture for the missions. The availability of capable, inexpensive launch vehicles changes the game as far as propulsion system on satellites are concerned. The answer is yes. With Deep Space One, Dawn, the commercial satellites, both in Europe and in the U.S., that are flying xenon-based propulsion systems, they are being really rapidly being added to the satellites. Both both for transfer orbit as well as station keeping on orbit, and hopefully we'll have more interplanetary missions along those lines to go along with the geo environment.
Are you really, when you come to talking about electrifying, I mean, obviously, satellites are powered electrically at the moment,
Right.
but I mean, obviously, on the aircraft side, we can sort of wait for other industries to progress the technology. I mean, the battery technology, we could just sit still and the battery technology will improve. It may not get to the density we want, may not get to the motor density, but it'll be in the right, it will all be heading in the right direction. Are you very much plowing a unique path when you're doing what you're doing?
Particularly in the power electronics, yes, because of the 20 kilowatts or so that we're looking at from a satellite standpoint, and then being able to use that in electric propulsion. The automobile industry here with the hybrid automobiles are really helping us as far as giving us more choices of sustained production of the electrical components that we've had problems with as far as obsolescence as we went through. So we're hopeful that as we move forward and can use some of those technologies, as well as hopefully aircraft use of more higher power electronics on aircraft, that there'll be a more stable base as far as electronics is concerned.
So here's just check the microphones. If Andy has a question, please step up. But with apologies to our European representative, the question is, what can the US do presently and in the future to prevent situations like what's happening to ULA now, solely relying on foreign technology? Now, it's very difficult. I mean, in the commercial world, it is a global industry, and it's very hard to divide up where it comes from. But it does go to the heart of where we spend or where we ask our government, or where we push our government to invest. And obviously, you benefited from it if GE or something like that invests. Could we have avoided the situation that we're in now? What would it have taken to avoid it? I mean, what were the reasons why we didn't think it was worthwhile in the first place?
Yeah, we did not want to avoid it. So in the Bush 41 and Clinton administrations after the fall of the Soviet Union, the directive guidance out of the government was, if you're a high technology company, look to the former Soviet Union and try to occupy their high technology businesses. You want to get those people off the street. And so that's what we did. If the United States did not buy the RD-180, somebody else would have, and there's no guarantee as to if that would have been a friendly actor or not. So that was the governing guidance. Even at the time we did that, the government said, look, we recognize that there's a potential for a cutoff of this supply of engines. So what we're going to ask you to do is maintain a 2 to 3 year supply of these to mitigate any kind of supply chain risk. And so we've done that. To fully answer this question, there was a 3-step process when we imported RD-180s. Step 1 was the Air Force said, once you get those things in country, we want you to take all of the technical drawings, translate those to English. So we did that. Step 2 was, now we want you to demonstrate co-production of some of the key components of that engine. In other words, in the United States, we want you to build some of these components and then simultaneously have Russia build some of those components to demonstrate that the two of you can work together to build the RD-180. And then step 3 was, now that you've done steps 1 and 2, go ahead and build an entire RD-180 in the United States. And in 2007, the directive came down that, you know what, the supply chain's working really well. It's a significant financial investment to build the engine in the United States, so we're not going to ask you to do that. We're just going to ask you to maintain a supply in the US of 2 to 3 years. So that was the plan all along. We intentionally elected not to do step 3. Right. And so now that Crimea has happened and everybody's in an uproar, we want to be punitive about it, so we're going to pay the price.
When it comes to the satellite side, obviously you live in a highly export-regulated environment, and I know that it's changing as they're trying to sort of clean that whole thing up. But do you worry that that because of that sort of vacuum bottle sort of thing that you sit in, that you're reliant on a US industry being as good as suppliers in other parts of the world, et cetera, to do your satellites or whatever, or something like that. I mean, are you worried that, that the US will fall behind in areas that you're working on? And, because the US won't buy a foreign component to put on a satellite, even if it's a better one,
That's not necessarily the case. We use many parts that are from Europe, Japan, in our satellites and even in the propulsion system. And they're used on government as well as commercial spacecraft. There needs to be competition in the world for key propulsion technologies, whether it's launch vehicle or commercial satellites or military satellites. There has to be competition to keep the price down, keep incentive for people to continue refining their business and make it a little bit better. And so what we have right now in the space area seems to be a fairly balanced usage of US as well as European and even in some cases Russian manufactured parts for our satellite propulsion system.
I wanted to dig a bit deeper into the integration thing because and even in your 2025 scenario, I mean, the airplanes look like they do today. The engines still hang under the wings, etc. But I mean, do we need to break? I mean, to what extent do we need to start breaking the barriers down between propulsion and airframe for your horizon?
Well, if you look at the installations that we've done over the last 30 years, even though it looks like a tube frame and the wings are the same and there's mostly two-engine aircraft, if you look closely at the installation through the use of advanced CFD, the engines have been able to get much bigger. The integration with the wing and the engine at the same time, the drag reduction, the overall weight reduction, there's been significant changes. It doesn't look like it. I think the next generation for the 2025 timeframe, in order for us to get to bypass ratios of 12 to 16, we can't do it with the design practices that we have today for inlets, exhaust systems, and thrust reversers. We will not be able to get that big a propulsion system on the airplane. So we've got to do things to reduce the drag, reduce the weight, otherwise we won't be able to get to that next generation. If you go to the next generation after that, I know you were trying to limit me, but on the unducted fans, it feels a little like Back to the Future for me. My first job was at McDonnell Douglas doing a demonstrator with the 578DX. I've got a picture of myself standing next to him. They're thinking, well, that's not going to be ready for 20, 30, or 40. And you look at those, and some of the regulatory engagements we've had around that kind of a propulsion system, there really are some common threads. How do we interact with the governments as we develop things? There is no way we could get to that next generation of unducted fans without proper interaction with the regulators. The kinds of ideas that they think that it needs to be in order to be safe just won't be feasible for the overall airplane to be an economic benefit to the airlines in the end. So I think there's a lot of government regulation work that needs to be brought forward, bring them close in as we're looking at alternate technologies and get them used to the idea and have them help us develop a different regulatory environment. It was, I think in the past when the industry was first starting, it was a lot more interactive that way when the regulations were actually being written, and the regulations haven't actually changed that much. It's how we comply with them have changed significantly.
So, which sort of goes to you, when you make, Sebastian, you mentioned about this, your distributed propulsion, where you have instead of having the engines under the wing, you have the power, the prime power. The generator is someplace, and the fans are someplace, and they're embedded in the airframe, and they're responsible for flight control, and you can do all that sort of thing. How do we get there? I mean, both from inside the company and inside the regulator, and both of you can answer this, but how do we achieve that? I mean, we've been talking about breaking down the walls in this industry for 30 years, and we haven't. Every new program, somebody says, oh yeah, it's because they didn't think about manufacturing when they did design. We don't break the walls down very successfully. How are we going to do this? And also really, I mean, I don't know if you can explore it or not, is, you have the engine manufacturer with his business model and his business case and his IP. You have the airframe manufacturer, and they're going to have to come closer than they are now. How are we going to achieve this to go forward?
The principle, so you were mentioning open rotor, yes, it's Back to the Future, but the principle is extremely good. What happened on this front is there was a creation of EASA engine and the EASA aircraft group. Then FAA joined the group. And actually those two pools of people were discussing what kind of rules could be applicable to those type of activities. But so the same principle would have to apply to anything which is different. The complex aspect, if you move to distributed propulsion, segregation between the thrust elements and the energy elements, is then the border is blurred. And you don't have anymore the FAA engine on the FAA aircraft. This will be difficult because they are part of the silos, I would say. And as soon as we are going to be discussing what kind of regulation is going to apply, I would say probably, if I had to imagine, with regard to the gas turbine which is providing the electricity, probably I would apply the same rule as for an APU. It's not a thrust element, but still it's a turbo machinery. But for the fans, it's a good question. We don't know. And we will probably have to put together the airworthiness people from both aircraft and the engine community together and try to cut pieces and say, okay, this will be called engine, and this will be called airframe. And that's why we start also at the bottom of the scale. The EFAN aircraft I was mentioning, this 10-meter aircraft, will be certified under light sport aircraft rules. And light sport aircraft rules, there have been already discussions about more electric capabilities there. But as I mentioned, if we were even in a 1-ton vehicle, we would not be able to certify it because there are no rules. And we need to learn from this first application of the vehicle to go back to their worthiness authorities, say this is what we have learned, this is the feedback that we have from in-service experience of the vehicle. Because everything new, they ask, okay, what is your database to substantiate any risk analysis, any safety analysis?
And how do we manage the industrial integration? How do we, I mean, do you have to replicate the expertise that lies inside the engine manufacturer and vice versa? Or is there a way to bring these two industries, these two pieces of the industries, and work more closely together?
I think there is. I think, when you look at the way the engine is architected and certified and where those limits are today, it's the fan case. And then we've got an inlet and a thrust reverser that gets tied to it. And there's a very specific fan blade off test that has to be done. And we do an enormous amount of work between the airframer and the engine manufacturer to get that structure integrated and certified. And I think we should be challenging ourselves to understand where those boundaries are. Does an inlet and a fan case really need to be two pieces of structure? Do we need to certify them separately? I think we've been talking about as an industry doing that for a long time, and to get to these higher bypass ratio engines that are higher drag and higher weight, we've got to figure out a way to get the weight out. And I think we need to have an industry panel similar to what you're talking about, where you do have both the engine regulators, the airframe regulators, the engine companies, and the airframers all working together. Can we redefine those boundaries and save some weight? Because otherwise we won't be able to improve for the next generation engines.
What about the integration sort of challenges you face? I mean, what are the challenges to integration that you face? And the things that you've got to overcome to start to combine systems or on the space there?
Well, it basically, we need to have a paradigm shift in understanding how, again, I'm a chemical propulsion guy. You open the valve, you get thrust. What we have to have moving forward is that we have to have the theoretical physicists, we have to have the AAA, we have to have the mechanical engineer, we have to have the person who understands the environments around the satellite working together to produce a spacecraft that can provide a very long life to meet our customer needs. So it's really a matter of getting all the disciplines together and start working at it. It's not a power problem. It's not a propulsion problem. It's a satellite problem, and we need to solve it as efficiently as we can.
Sebastian made the point earlier on. He was talking about bringing in young people who do not have the same boundaries in their thinking. I mean, is that what we have to do? We have to wait till we age out to get this thinking.
Well, some of us are set in our ways as far as how we solve problems, right? And that's one way to do it. Another way to do it is simply to empower a team to go off and work it out. Engineers are famous for being extremely creative when we allow them to get outside the box, not just tell them to. And I think it's a part of it is it's empowering the folks to go off and present them with a problem and have them go off and be successful solving the problem.
Now, do we have to change the customer as well? I mean, do they have to become as integrated? I think Sebastian made the point is that the regulator is a safety brake. He's right. Sort of like a checks and balances saying you're going too far. You're not. The customer has to be a bit more agile than he is today.
Right. With the Air Force and aerospace oversight as well as JPL, we have very, very educated customers. That a lot of the education has to be done within the companies that have been building the same thing over and over again for the last 40 years to take on a new perspective as far as how we move forward. In our industry, it's not so much regulation as it is just, hey, we've always done it this way, and now we have to break that mold and do things differently.
We had another question. Anybody with a question? There's another question which is very pointedly at you, Les, and that was basically the question is what precludes ULA from, I think this is to do with the market, the world market that you saw, and it's really around, what stops ULA competing with Arianespace for a larger part of the world market? I mean, why can't you be competitive on price and take a larger part of the market and justify the cost of right. that new engine?
So the answer to that is ULA can compete with other companies. We cannot compete with a country. So Arianespace, if they are highly subsidized, that is a marketplace we're not going to be able to enter. There's just no way you can do that. I can advertise a low price on one of my launch vehicles. The Russians will come in with a lower price on a Proton, and then ultimately the French will come in with the lowest price on an Ariane, and that's just the way the commercial market's been going so far.
Obviously, the environment's a big thing on the commercial on the aviation side. But you made a good point, John, about it's a driver in your side of things as well. I mean, more to do with the hazardous handling. I mean, I don't know whether in ULA whether you really face with rocket launches whether or not there's environmental pressures on you to make changes or improve things. Or...
Yeah, I mean, not really on the launch vehicle side. I guess in the mid-1990s, 70% of all of the Air Force's environmental violations or filings against the Air Force occurred at Vandenberg Air Force Base out of Santa Barbara. But typically, launches, rockets are just grandfathered.
Yeah. But it is something that you continually have to work on the satellite side.
It's a significant cost associated with getting the components for propulsion systems delivered. And then getting the propellants to the various launch sites we've got around the world, and then fueling them and getting them ready for launch. It's a significant cost associated with satellite, and if there are ways around them, and we hope in the coming years that there are alternate options for this, then that will make you a more competitive product in the marketplace.
Okay, so I think we're being told to wrap up here. So, folks, I wonder if it's an interesting, we had two very different sides of the industry here, and it's very interesting to sort of compare and contrast, and in some cases, link the problems between the two. So I want to thank you very much for doing that, for coming with us today. I do have to give you your prizes for attending.
Oh my gosh.
Which are the coins. I don't know whether or not they get you something in the bar, but you can try. This is the AIA's coin, so thank you very much for that. So I appreciate it. So thank you very much, folks, for your great panel. Thank you.
Thank you, Sebastian.
Thank you.
Thanks, Sebastian.
Thank you.
Thank you.